Alright, so we're looking at Newton's second and third laws today. Once we get through the second and third laws, I'm going to tell you now, tomorrow what we're going to begin are just difficult problems. Okay, that's what we're going to start doing after this. Once we get through all three of Newton's laws, we're going to look at some difficult problems. The problems are going to be on inclined planes. The problems are going to be objects moving in different angles, moving at different velocities and accelerations. So they're going to be tough. But we're going to spend a few days just going through example problems, okay? Today we're going over the theory.
Oh yeah, just a general question. Like for the test, I think it's like next week, Tuesday.
It's on the 30th, I think, right?
Yeah.
30th? Yeah.
So are we gonna have to know like Newton's laws, the problems, and then like sine and cosine? Or? Yeah.
So the next test, remember, is where we left off. So you're going to need to know the sine, cosine, and projectile motion stuff. That's the beginning of the test, which is probably the tougher stuff. Then we're going to move on to all the three sections of 4.3. And then once we finish this, 4.4 is looking at those example problems. We'll definitely finish that. So your next test is going to be pretty much the end of chapter 3, projectile motion, and all of chapter 4. Okay? So give you an idea. Alright, so our two objectives today are to describe acceleration of an object in terms of mass and an external force, and to identify and explain what are called action-reaction pairs. Okay, those are the two things that we're going to look at. Let's take a look at the first thing. First, what we're going to do is, and we don't usually do this, or most teachers don't usually do this, but I'm going to try and show you where Newton's second law comes from. So let's take a look. We have a set of data from what's called a spring scale, and we have a motion detector. And a spring scale, what it does is it measures the force on an object. So let's say we have an object, and we're given a bunch of accelerations of that object, and the force that causes that acceleration. So remember, if I push lightly with my hand on a book, it goes slowly. If I push with a higher force, it moves quicker. So we know obviously right away that there's some correlation, right? The more force you apply to an object, the faster it will move. So we can see there's some sort of a correlation. What do you see the correlation as here in this example?
So it's like the more Newton's applied, the faster the acceleration. So like
Yeah, the more Newton's applied, the faster the acceleration. Specifically, Olivia, for this example, do you notice what it is? Look at the numbers. What is it? Triple. You're going to say triple, Paul? Very good.
A equals 1/3 of m.
Yeah, very good. A is always a third of the net force. Well done. So our factor here, we're going up by a factor of 3, or it's 1/3. Very good. That's our factor we notice. And for all of these, we can see that they're the same, right? So here's how we write this. And this is going to be a little bit weird. Once we get the actual formula, you don't have to memorize all I'm doing now. But I want to show you guys where it actually comes from. What we say is this. The force, this force, is proportional to the acceleration. So I put some value k there. And k is called my constant of proportionality. Again, I'm showing you where it comes from. You're never going to have to prove this on a test, but it's good to watch and understand it. You can write it down if you like, that's fine. Or you can watch. So k is some factor. Now, the way I can figure out what k is by looking at my units. So let's start by writing out my units. What are the units of force? Newtons. So let's do this. Let's write Newton equals k, which is what I'm looking for, times the acceleration units, which are meters per second squared. Very good. So we've got Newton equals some constant times meters per second squared. How do I get rid of a fraction? Multiply by the? What's the word? Reciprocal. Reciprocal. Be careful. So let's multiply both sides by second squared over meter. So, cancel. Cancel. That's negative reciprocal is perpendicular and parallel lines. Right?
Wait,
So-
you don't just times it by seconds squared? Like
Second, and then you would divide by meters now. Afterward,
yeah.
wouldn't you?
Oh, yeah.
So I'm just doing it all in one step.
Got it.
Whenever you have a fraction, just multiply by the reciprocal. Now, what happens is this. The units of k become second squared times Newton over meter. But that doesn't look familiar. So that doesn't really help me with what k is. But if you remember and look back in your notes, I told you what a Newton is really. Go look at your notes. Flip back. Try and find what we said in Newton. Moms?
Newton
Jack Jones Street Jet.
KGM over,
That's less than that's
Good.
What? Where was it?
everybody take a look.
Easy, easy.
The units of a Newton were kgm over s squared. Now remember, this minus sign is a hyphen. It's not a minus sign. Remember that? These are really multiplying the units. So take a look now. Watch what happens. Seconds cancel with seconds. Meter cancels with meter. What am I left with?
Kilograms.
And what are kilograms? What do they measure?
Mass.
What do they measure?
Mass.
Mass. So really, if I go back here, this was really force equals K is really mass. And if you remember from middle school physics or physical science, F equals ma. This was one of Newton's laws, F equals ma. This comes from this being proportional and the units matching up. So this K that we were looking for, this constant of proportionality, is really just a mass. So this is what you want to write down. The sum of the forces equals mass times acceleration. Sum of the forces equals mass times acceleration. Okay? That's what we're writing. And where does that come from again? That comes from this original equation up at the top that we started with. Once we derived the units of K, and those units became kilograms, we realized that K is really just a mass. So K was some dummy variable. It's called a dummy variable because it's any variable that it can become. Not dummy as you would think. Dummy meaning any variable.
You don't just say that.
Okay.
I don't say that.
That's not nice.
Any questions on this? Now, that's what I want you to remember. If you look in your textbook, this is how you're going to see Newton's second law written. An object's acceleration is directly proportional to the net external force. That's where this comes in. Acceleration is proportional to the force. And inversely proportional to the mass. So the mass goes in the denominator. And then rearranging it, you get F equals ma. So that's what Newton's second law really says. If you want to write that down, you can. It is good to know. But if you know F equals ma, you're fine, okay? If you want to remember F equals ma, that's what you really need to remember. And one thing I do want to note is that this is dependent on the directions. So if you're looking at all forces acting vertically, or in the y direction, then you're looking at the acceleration in the y direction. So this can be written as this. And this. Remember how we, in projectile motion, break up the x direction and the y direction? We're going to do the same thing with forces. So it might be useful to write this like this. And I'm going to add that to my notes right now. I've got to put that on there so you guys can see that. But we're going to definitely do that. Okay, just so you know, we're going to bring it to notes.
Max Cox.
Any questions? Any questions? There's Max's name, yes.
Hey. Very clever.
All right, let's go to some examples. The examples are so simple, you guys are going to kind of laugh at them. All right? Again, we're just doing basic stuff today. It's going to be very basic.
I like it.
You like to laugh at them? Good.
I like laughing
The people? So,
No, it's a sword.
the question says the following. Space shuttle astronauts experience accelerations of about, relax guys, 35 meters per second squared, which is almost what's called 4 Gs. And a G is just any multiple of 9.81. So 2 Gs, not 4G like your phone, guys. 2 Gs would be 19.62, you just double the 9.81. So what's happening here is that the astronauts, when they leave, feel like their body weight is almost 4 times what it is. Imagine feeling like, so let's say we weigh 150 pounds as an estimate for an average weight. That means you would feel like you weigh 600 pounds suddenly. That would feel like a lot of stress on your body, wouldn't it? For every day feeling like 150. That's what they undergo. That's why they need to train for this stuff, so that they don't actually get what's called a red out, where they start to, all their blood rushes to their extremities, they pass out. Like that example of the roller coaster I talked about. Okay? Hold on 1 second, let me just finish the reading. Almost 4 Gs. During takeoff, What force does the 75-kilogram astronaut experience during this acceleration?
Oh, it's also.
Okay, during the acceleration. Jack, tell me what you're going to answer.
So is 74 G's a lot then?
Yeah.
I want to go with those G's.
So you felt 4 times your weight at one point on that run.
Wow, Jack.
Yeah, I went to
Wow.
like spinning round and round. Like
The
it was,
Incredible Hulk?
Wow.
The Jeep up to Disney, yes.
I went to Disney World and like 60 rounds and round. It's like something like seeing like space.
How many G's is it?
Like it was like real like it simulated space. I don't know.
So you may not have done that.
No, listen. And
Let's listen to Max, guys.
it like spins you around really fast and stuff.
Yeah, I know. And it pushes you up against the wall.
No, not that one. It's like
That's the gravity
it's
triangle.
That's in like
Yeah.
the 60s.
It's like this one you go into like you have to be like at a certain age. Like you go.
It simulates outer space, yeah.
Yeah.
It's
The reason, guys, the way it works is when you spin in what's called centripetal motion, we'll talk about this when we get to circular motion, you experience a lot of acceleration in your body. That's when they spin you circularly to give you that feeling of a certain amount of G's. And we'll go into that. Okay?
No, you're like buckled in and stuff. And it's like,
I know what he's talking
you
about.
see like you see like space in front of you. It's like,
I don't think space.
The one you're thinking about is when you have a circular object here and you're against the wall to start, and then eventually you start to get sucked against the wall, where you could actually like just like float. That's that one. He's talking about when you're sitting in a seat
yeah.
and you're moving in this like turbine almost.
There's like a green and orange. My
Yes.
sister went in the green.
There's like a green and orange.
So let's take a look at this problem, people, quickly. Formula, everybody. What did we just say the formula is?
F equals MA. F equals
Okay.
obviously.
My givens. F, we don't know. M,
75 kilograms.
and what's A?
35 meters.
So is this the easiest problem ever? Yes, it is. Multiply and get your answer. Okay, plug in, please. Yeah, and that's what we're going to talk. The next one we're going to do one's a little trickier. Third one will be even more trickier. But then we're going to use these problems with like inclined planes and stuff where they get more difficult. But we need to understand it basically first, so we can go on to the more difficult stuff. Multiplying these two quantities, we get 2, 6, 2, 5. What are my units of force? Newtons. Okay? Multiplying 75 by 35, we get newtons. I'm going to move on to the next one. A bowling ball, initially at rest, please stop talking, is dropped from the top of an 11-meter building. It hits the ground a second and a half later. Find the mass of the ball. God bless you. Find the mass of the ball. If the net external force is negative 74 newtons. Okay, negative 74 newtons. So let's draw a diagram of this one, please, just to start. We have a bowling ball. It is dropped from rest, so it moves downward until it ends up at ground level. We know that its height above ground is 11 meters. And what should I put here? How many meters is it really?
Negative 11.
Good, because it's moving.
Down.
Good. Notice it is moving down also. We see the force happens to be negative. We know the time period it takes is 1.5 seconds. We're told that the net external force is negative 74.
You need gravity, right?
Okay?
Acceleration.
We need acceleration, don't we? Because remember, our formula is this. What do we want to find? We want to find the mass. We've got the force. Check. We need the acceleration.
Or negative 9.81.
Good. You didn't fall into the trap. Very good. Everybody tries to use all this information to find the acceleration. If it's free fall, you don't need it.
You don't need it.
Because in the y direction, AY is always negative 9.81. Now, you can verify that, and you can solve this, and you can do that. That's fine. But there's no need to use this information. What do we call information that we don't need?
You
Sure.
stupid.
What's the mathematical term for useless information?
No.
Just Joseph, answer. Not useful.
If I have money that I'm not going to spend, it's what money?
Savings.
What is it?
Qualified.
Excess or extra money, right? So, information that is not used,
Trick question. What's the?
extraneous. Very good, Masha. Extraneous. I heard extra.
I get this straight.
That's
I heard
like the same.
excessive. Sorry, I didn't hear. So, extraneous. Now, I know acceleration, I know the force. How do I solve for the mass, everybody?
Divide by acceleration.
Divide by acceleration, please. Basic math. It's alright, there we go. What do you notice? The force is negative. Isn't the acceleration negative? So you get a positive mass. You can't have a negative mass. So what can we conclude, by the way? If the force is negative, the acceleration must also be. If the force is positive,
Then the positive.
so let's make sure we write that correlation down. The force and the acceleration will always have the same sign. The net force and the net acceleration will have the same sign because mass has to be positive. You get 7.5 approximately?
Wait, what did I see to find y?
Y is negative 1.
What did I ask you to find y?
We'll do those kinds of problems where given forces, we have to determine from the force we can find the acceleration, and then with the acceleration we can find the y or the x value.
That won't
Then
be
we have to go
on
back
this.
to kinematics.
That won't be on this.
That's tomorrow. We're going to go into those kinds of problems. Yeah. Right? You're a day ahead of your game there. Yeah. 7.5 kilograms. All right. Next problem. An object accelerates from a velocity of 6 meters per second to 15 meters per second in 10 seconds. If the object's mass is 25 kilograms, what net external force must be applied to accelerate this object? So good, Jeff. We're trying to find the net force right away. We're trying to find the net force. Let's list some givens, please. Tell me what some givens are for this problem, Max.
The initial velocity is 6 meters per second. The final velocity is 15 meters per second. The time is 10 seconds, and the mass is 25. Oh, and acceleration, I guess, is negative 9.81.
Be
Meters per
careful.
second squared.
Be careful. The problem says find the acceleration, doesn't it? Does it say it's moving vertically, Max?
No.
Everybody, look at this, because this is careful here. It doesn't say that it's moving vertically. If it were moving vertically, the answer is just negative 9.81. You're done with the problem. You're definitely done. But it doesn't say vertical. It just says it's moving, right? So we can't assume that. Now, what net external force must be applied? If we want the force, we need the mass and the acceleration. Well, we've got the mass. But we don't have the acceleration, but we do have other information, don't we? So tell me, what formula might I use to find the acceleration? Good. A is delta V over delta T. Well done. Remember this formula? Acceleration is the change in velocity over the change in time. So I've got Vf minus Vi over T. T is just 10, so I don't have to put delta anymore. We're going to get 15 minus 6 all over 10, which gives me 9 over 10, which is 0.9. That's my acceleration. Now, I didn't put units, but what should my units be? Good. And I know that that's correct because I have meters per second over another second. These are meters per second up here. This is meter per second over another second, yielding meter per second squared. So that's my acceleration. Am I done with this problem?
No, sir.
Yeah, so plug into your formula now that we've got acceleration. F equals mass times acceleration. And notice how it's 0.9 and not 9.81? It is different from gravity's acceleration. What do we get here?
22.5.
Thank you. Paul, very good. Units of? Newton. Very good.
That's a ton of newtons per centimeter. That's good.
Okay, 22.5 newtons. 22.5 newtons. So you see how kinematics, and this is a basic problem still, but how kinematics and our equations that we've used in the last chapters do play a role throughout the year. We're going to continue to use these. That's why chapter 2 and chapter 3 that we learned are so important, so vital. We'll use them later on as well with other topics, okay? So keep them in the back of your mind. All right. Let's take a look at Newton's second or third law, rather. I've given you guys the summarized version of Newton's third law. I don't believe that what the book tells you is very useful to memorize. It's very long and tedious, okay? The definition they give you is just, I don't want to use the word annoying, but it kind of is, okay? So simply put, for each action, there is an equal and opposite reaction. For each action, there is an equal and opposite reaction. Oh, thank you. Very good. How did that didn't come up? I guess Newtowns is a
Newtown. Oh, that's not a
typo, yeah. Newton, sorry.
Sorry, I wrote it the right way.
The board is not oriented, guys. Get rid of that W. It's not Newtowns, it's Newtons. Okay? Anyhow. Let's discuss. So, how come when I stand here, I'm not moving? What's happening to me right now?
Gravity's pushing you down. The
Say it again?
Gravity's pushing you down, but the force is pushing you up.
The floor is pushing me up. Gravity is pushing me down, but the floor is pushing me up. So my action is down, right? The action is gravity pushing down. What's the reaction? Floor pushing up.
But is the floor like really pushing you up, or is it just keeping you up?
It's pushing you up, Jack.
Here's how I think about this. If I'm not moving, my velocity is 0, right? Therefore, I'm in a state of equilibrium. If I'm in equilibrium, my forces must be balanced. So if my weight is X amount of newtons down, then the floor has to result or react with a force of X amount of newtons up. So for every action, there's an equal and opposite reaction. Now, this can become a little bit misleading. So what I want to discuss is this. I want to think about a nail being hammered into the wall. Okay? So imagine you got the wall here. You've got a nail, and I'm going to draw a zoomed-in version of the nail. You've got a hammer over here. About to hit the nail into the wall. Now, I know it's terrible drawing. So,
That's pretty good.
thank you. Now, the idea here is this. People think that this, when it hit, because it has an equal and opposite reaction, is in a state of equilibrium. But clearly, who's hammered nails into a wall before? Anytime ever. Or done something like that. Okay. The nail moves, doesn't it?
It does.
The nail moves. And, listen guys, please listen. The nail moves, and it moves at a very quick pace. So it must be accelerating into the wall. So this can't be a state of equilibrium. But there's still a force and there's an action-reaction pair going on here still. So here's what I want you to think about. The nail pushes into the wall pushes back on the nail. Right? The nail pushes into the wall, but the wall pushes back on the nail. Now, the hammer pushes on the nail, and the nail pushes back on the hammer. The issue is this. Remember from physics, if I want to think about an object, I want to draw only the forces acting on it, what we call a free body diagram. So let's draw an FBD of the nail. Let's go ahead and draw an FBD of the nail. Somebody tell me, what forces are acting on the nail? On the nail. The hammer in the wall. So I've got a force here. I'm going to say force due to the hammer. I've got a force acting back on the nail. Force of the wall. Okay? Now, these are not action-reaction forces, though. Because the action-reaction is only apparent if you draw 3 free body diagrams. There's my hammer. Here's my wall. On the hammer, On the hammer, what we have, okay, is the force of the nail acting back on the hammer. On the wall, we have the force of the nail acting on the wall. So this force of the nail, and watch what I'm going to do, this force of the nail acting on the wall and the force of the wall acting on the nail is an action-reaction pair. They are definitely equivalent. Next, the force of the hammer on the nail and the force of the nail on the hammer are also an action-reaction pair. But they are not necessarily equal to one another. So let's say, for example, the force of the hammer happens to be 10 newtons. Well, then the force of the nail on the hammer backward is negative 10 newtons. But that does not necessarily mean that these are 10 newtons over here. So the wall might be exerting a force back on the nail of, I don't know, let's say 4 newtons. And then this exerts a force of negative 4 newtons. Oops. Relax, relax, we'll discuss. And by the way, let's switch this negative sign over here to be indicating our direction, just to know that they're opposite. So,
Wait, but I thought, so force of the hammer is negative now?
because it's acting left, and left is negative.
Right,
Yeah, just to be
right.
consistent with direction.
I'm sorry.
Focus. So, on the right side here, we have the hammer hitting the nail with a force of negative 10 newtons to the left, and the nail reacts with 10 newtons to the right. Over here, we have 4 newtons from the wall acting on the nail, and 4 newtons negative from the nail acting on the wall. So if I were to just look at the nail, now just look at the nail. The only thing acting on the nail is this negative 10 and this positive 4, coming from this acting on the nail and this acting on the nail here. So if I were to look at the nail, what would the net force be on this object? What would it be? Negative 6.
Wow.
So
Impressive.
the F net on the nail is negative 6. Now, if the net force is negative 6, the acceleration must also be negative. Which makes sense because the nail is moving to the left. And remember, F equals ma. I know this is negative 6. If I want to find the acceleration that the nail undergoes, all I need to know is the mass of the nail now. And I know what the mass of the nail is, because I can measure it on a scale. So if the mass of the nail were, say, a quarter of a kilogram, you just put in 0.25 there, and then you can find the acceleration. So it seems like a lot of students have the tendency to think about things being in equilibrium because it's action-reaction. Well, this is the action-reaction here, and this is the other action-reaction. So you hit the nail pushes back. That's one action-reaction. The nail hits the wall pushes back. That's the other action-reaction. Jack, and then Raj.
Sorry, what's F what?
F net.
F net. The net or overall force. F net.
And so what does the 4 newtons represent?
The 4 newtons over here represents how much the wall pushes back with. If the wall could put, God bless you, if the wall could push back with a full 10 newtons, then the nail would not be able to exceed the strength of the wall or, break into the wall in a sense. The wall would withstand it. And that's the way you can think about this. Try go up to a concrete wall sometime soon and try and nail into a concrete wall. There's a good chance it's not going to work right away, especially if you don't have the right nails and the right tools, right? Because the wall, because the wall would push back with a full 10 newtons, which would make the F net 0. Again, think about this. If the wall pushed back with 10 newtons, everything would have been balanced, and everything would have been 0. Therefore, the nail would not go into the wall, because there's no acceleration there. If the overall force is 0, then there's no acceleration, so the nail does not move. It doesn't go into the wall. But clearly here, the wall we have cannot extend or cannot sustain the force being applied to it by that nail. So because the nail's force of 10 newtons overcomes the wall's force of 4 newtons, we have the nail going into the wall, or accelerating into the wall, with a force of negative 6 newtons. Okay? one last thing to discuss. One last thing to discuss. Well, that's our diagram, first of all, of what's going on in the nail. Okay? Last thing to discuss. And you don't have to write this down while you think about this, though. This is a little bit intriguing. You have to use some theory here. If you like those shows, like, have you seen those shows like Through the Wormhole or The Universe on like Discovery Channel or History Channel? They have a lot of these science shows. They're really cool to watch.
Mythbusters.
Okay? Mythbusters, another good one.
I watched that, that's.
All right. In section, listen, in section 4.1, we talked about field forces and contact forces, okay? And we said examples of field forces are forces that are acting at a distance. So for example, if I were to push, like, Molly's pencil case here, that's a contact force. But if I were to take a magnet and put the magnet up to a pen and pull the pen this way, that's a field force, because you don't see the force acting there. Now, field forces also come in pairs. They have action and reactions, and most people don't realize that. And the easy way to remember it is this. If I were to take this Purell bomb and drop it, what's pulling it to the ground here? Gravity. Now, gravity is a force, and forces come in pairs. So if I were to drop this, the ground or the earth is pulling on this bomb. So here's how I draw it. Here's the earth. Here's an object being dropped from some elevation. Let's make believe it was the skydiver from last week, okay? Felix, whatever his name was, that did a free fall. So, Felix gets dropped. He does a free fall. So the earth is pulling down on him with a force due to gravity. That's what pulls him toward the earth, right? Well, I just said a minute ago that every force has an equal and opposite reaction. So he must also be pulling the earth, right? With the same force. So he is pulling on the earth with a force upward of Fg. Or Fb for the bottom, okay? Now, why doesn't the earth move? Why does Felix move and not the earth? Tough to think about. Masha.
It has more inertia.
Good. Inertia helps us. Very good. This one, the earth has much more inertia, or the tendency to stay still, because inertia is the measure of mass. Very good. So it wants to stay still. Why else?
The Earth has way more mass than Felix.
Okay.
Yeah,
So, extrapolate or keep going. The earth has more mass.
It'd be like, it'd be,
What's your equation for force and mass? We just did it.
You know.
yeah, NF equals,
Thank you, Tyson. MA, very good.
Yeah, mass.
F equals MA. Okay. So let's stay with this, guys. Make sense of this. Both of these F's are balanced, right?
Yeah.
Because they're pairs. So let's assume F was 10. I know it's not, but let's say it's 10. So for Felix, we have 10 equals Felix's mass times Felix's acceleration. For the Earth, we have 10 equals the Earth's mass times the Earth's acceleration. So, which mass is larger again, the Earth or Felix? The Earth, clearly. So, if this value, let's say that the mass of Felix is 5, what would the acceleration be, everybody?
-5.
-5,
Imagine we're not free falling, guys. Let's just say this was the example. 10 equals 5a, solve for a.
Oh,
2. Okay, let's say the acceleration turned out to be 2 here. Well, if Felix's mass is 5, what might the Earth's mass be? Some much larger number, right? So let's say something like 5 million, right? Think about the Earth. We have no idea, we know, but we don't know off the top of our head what the Earth's mass is. So let's say it's 5 million, whatever the units are. Just some very large quantity. If I divide 10 by 5 million, what is my acceleration going to be? Very what?
very large. It's small.
Small. Again, guys, divide by 5 million. To solve for a, you would divide both sides by 5 million. You would get 10 over 5 million. That number, you're dividing by a very large number. Therefore, it will be a very small acceleration. So here's crazy to think about. Ready? When I dropped this marker, or when Felix dropped to the Earth did move, but with such a small acceleration that it was negligible. Again, I dropped this marker, causing it to accelerate downward. The Earth accelerated upward, but because its mass is so large, the acceleration the Earth undergoes is almost non-existent. It doesn't really occur. And at the same time, objects are moving all around the Earth, right? So a lot of those objects are also balancing each other. So really, gravity comes in pairs, and the Earth does get pulled upward every time you fall down. Every time you drop an object, the Earth is moving up, which is kind of crazy to think about. But it's moving up so infinitesimally small that it basically does not exist. Infinitesimally just means infinitely small.
I'm going to use
Okay? Infinitesimally
I'm going to use
small.
that math today. Mr.
Any questions on this, guys? The ideas from today, two things. First, F equals ma. Again, sum of the force equals mass times acceleration. Second thing to remember, every action has an equal and opposite reaction. That's why when you walk forward and you push, you're pushing, and the force of push is exerted or coupled with the force of friction moving you forward. There's friction between your foot and the ground causing you to move forward. Okay, very good.
Thanks.
You push down the trampoline pushes back on you. When we study trampolines, when we study springs, we'll talk about trampolines and how they're really a spring. Now, besides this, take a look, people. Two things. First, do not back up yet. We're not done. First, homework. Homework, write it down. Second, over the last 4 days, I hope some of you saw the homework. If you didn't, there is a video you should watch. Watch the video for the lab for part 4. All you have left right now for your lab is part 4. If you watch the video, I guarantee you it will be very easy to do part 4. Okay? I'm telling you now. Say again?
Did you watch the video then?
Yeah, I watched the video and tried it, and
Okay.
not the dark.
Guys, before you go on, because that's a good point. The values that you got in the lab are not going to be identical to the values you get mathematically because of discrepancies. They should be close.
No, they're
They
not.
should be close. They're not close, come show me for sure. It's not a problem.
When's the last due?
I think we'll do the lab on Wednesday or Thursday, so work on it tonight, but we'll talk about tomorrow, either Wednesday or Thursday.
Wait, the lab's due Thursday? So Jeff, Alright, so Wednesday night.